Hello, um, hello everyone. So, hope I am audible. So, welcome to the week 3 of this course titled Defects in Crystalline Solids, Part 2. This is a course by Professor Shashank Shekhar from IIT Kanpur, belonging to the Metallurgical and Materials Engineering Department. So today is the week 3 of this course. So in the first 2 weeks we have learned about the dislocations in FCC and BCC and also in HCP. So today we will move into the ionic system. So let's get started. So this is the course outline. Okay, so this is the week 3. We will be talking about the ionic systems and the dislocations in the ionic systems. So we have the ionic structures. We will learn about ionic structures, the different type of ionic structures like B1, B2 and etc. There are many more. Then also superlattices. So what are superlattices? What is the criteria? And how are superlattices different from ordinary lattices. Then we will learn strain hardening or work hardening, also called as cold working. So we will learn that, and also we will solve some assignment problems in the end of today's session. Okay. So, we started with a very simple. So we started with very simple systems, like FCC or BCC, which is the face-centered cube or the body-centered cube. Then we moved on to more complex systems like HCP or hexagonal flow spec. So like still today, like research is going on about the hexagonal systems, and there is yet a lot to learn, a lot to understand more about hexagonal systems. So like our understanding is still very limited, but we saw that many things in HCP are similar to FCC. Okay. Just I will check once whether my recording is going fine or not. Okay. So okay. So now the ionic crystals. So what are ionic systems? So like if I ask you that what is the most common ionic system which comes to your mind? So then what will you say? We will say table salt, right? So table salt or rock salt, which is also called as NaCl, right? So it is sodium chloride. So what are ionic crystals? So in ionic crystals, so they are crystals where the in the lattice position, so they are made up. They are sitting the ions. It can be metallic or non-metallic, but there are electronic charges associated with each atom. And now when dislocations will arise in ionic crystals, then what will happen? Then depending upon the type of dislocation and on the plane on which the dislocation is moving, there may be a net charge on the dislocation, or there might not be any net charge on the dislocation. So we will look now in that. So what is the important thing here? So the important thing is that depending on the type of dislocation and on the plane at which it is moving, there might be a net no charge, or there may be net some charge on the dislocation. Okay. So NaCl, so this I talked about. So we will talk about the rock salt structure now. So it is so as we will see later. So it is basically two interpenetrated lattices. So yeah, sodium chloride is basically two interpenetrated face-centered cubic or FCC lattices. So if we dig further, then we will be able to realize that it is nothing but a simple FCC system. And in this why this interpenetrating FCC structure is so important. Like, why are we studying this? Why is it so important? Because here the sodium is charged plus and similarly chlorine is charged minus, and because there is a interpenetration of two lattices, so in this interpenetrating system it is not the usual FCC slip system which arises in this sodium chloride lattice. So we will look into it in great details. We will understand it with the help of figures and schematics. But what is important you have to remember is that although it is a it consists of two interpenetrated FCC lattices, but it does not follow the usual FCC system. Okay. Okay. So this is the sodium chloride structure. Okay. So this is sodium chloride. So this is like a picture I just took off the internet. So how to understand this structure? So let us uh, try to understand the structure. So if I ask you that in sodium and chloride, so if we assume that these ones are the sodium, which means that the pink ones are the sodium atoms. So we will see that where are they sitting. So we will count. So if this is 1 and this is 2, so we can take this, we will take this whole box as the unit cell. So 1 2, then we have 3 and we have 4, then we have 5 6 7 8. So we have these 8 atoms sitting at the 8 corners. Now we will see that in for each face, at the center of the face also one atom is sitting. So if we count them, so we use as 1, then 2, 3, 4, 5, 6. And so if we don't want to like confuse, we can give them a dash, 1 dash, 2 dash, then 3 dash, 4 dash, 5 dash. This is 5. Huh? This is 5 dash, 6 dash. Okay. Now if so we are done with the sodium. Now what about the chloride? So you see, so this here is the chloride. So this it might be difficult to imagine from here, but this is also an FCC. So if we consider this as the edge of the lattice of chloride, and if we extend this, right, we can extend this like this. So I will not draw the full thing, but here you see, here is the chloride, right? So what is sodium? So sodium will be Na plus, and chloride will be Cl minus. So here is one chloride, right? So okay, so let me change the color, then it will be easier for you to understand. So just let me change the color. So if we consider this now, so if I start my point, so this is your 1, and then where will this go? So this will go in the, it will extend in the backward direction like this, right? So this one will also be green actually. So no. Okay. So if I one second. extend the lattice like this. Okay, so here is one chloride, then here another chloride will come, right? So this will be number 2. Similarly, here another one will come, so this will be called as number 3, and then this here will be called as number 4. Now in this phase, this one is sitting in the middle of the phase, right? So where this was, this is the middle of the phase, so this will be your 1. So if I call it, it's 1 prime. I want to keep the ink annotations, right? So what we are seeing is, so one second. So we are in green. So in this phase, so if I like extend this lattice like this, so what will happen? So it will, second. Yeah. So if I extend this lattice like this, so here also the chloride atom, the chloride ions will sit, right? So here we have the 2 atoms, and then here we have the 2 chloride atoms, right? And then we see that this is sitting. So in this way we have to imagine that if we extend the lattice, then this lattice is actually a combination of 2 separate FCC lattices, and means all the sodium plus ions is making one FCC lattice, and all the chloride minus ions is making one FCC lattice, and they are clubbed together. So we are done with the chloride. So this is how the rock salt structure is a mixture. These are 2 interpenetrating FCC lattices. Okay. So then what is the slip system here? So here similar to, so there are 2 things here, right? So when we talk about dislocation, so there will be the slip system and there will be the shortest lattice vector. So the shortest lattice vector is similar to what we observed in case of FCC, because if you look at the top from any top face, so like so here if you consider this face, right, and if we look from the top, then this will be the shortest lattice vector, right? So the shortest distance between 2 atoms is same, so it is half of 110, because it will be this will be the shortest lattice vector. Okay, and then the slip system, so the slip planes for this one will be, so it will be 100, 100, 110, and occasionally we may actually end up seeing the 111 slip planes and even the 112 slip planes, but they are very rare. Okay, so then if we are talking about the dislocations in this interpenetrated system of NaCl, so how many extra half planes will be there? So this is the question now, that how many extra half planes are there, whether it is charged, whether it is uncharged, so we will look into them. So if we look from the 100 direction, right, so you understand the 100 direction means we are looking from the top. So look from the 10, so if we look here, then so this is like I have drawn, so these lines, so these are nothing but the guides or the guidelines which help me to draw, so don't think it as planes or something. So looking from the 100 direction, so what are we seeing? So we are seeing that if this is the plane, right, then this plane and this plane, so this is the dislocation, right? So here we are looking same, so we are looking from the 100 direction, and these are the Berger vectors. So what we are seeing is basically alternating layers of atoms with opposite signs, right? So we are seeing alternating, so here it was plus, then it is minus, then it is plus, then it is minus. So we are seeing alternating layers of atoms with opposite signs, so in along this direction. Now here see in the green plane, so the green plane is what you see, it's all positive, right? However, the planes which are to the left and the right, so if we see, so what we see is that there are three planes here, and on the bottom there is only one plane. So we have these three planes here, 1 2 3, and on the bottom, so here there is only one plane, right? So here two planes with opposite charges are missing on the down, right? So one thing to realize is that H dislocation is now clearly different from a non-ionic, for example metal system, aluminium, because here we have two planes missing. So how many extra half planes are here? So here is this forms this portion, so I have marked already. So this portion forms what is known as the dislocation core here. This is what? This is the direction of the Berger vector. Right, so and there are in ionic systems there are two extra half planes. Now the question, so we learned that there are two extra half planes. Now the question is that is the dislocation core charged? So what do you think? So is the dislocation core charged or not? So we will understand that. So the answer is that no, means the dislocation core is not charged. So why? So we will look into this. From here, looking from this 100 direction, it may look that the core has a net charge, but what happens in the layer below it? So here we have what we have drawn. So what we have drawn is a 100. So these are alternating layers, right? Now behind this is the opposite charge. So behind each electron, so behind each atom that in the charge there is an atom of opposite charge, means of oppositely charged, and that is what. So actually what has happened is the in the dislocation core the charge has reversed, like right in this layer it is minus, but in the below layer in the it will be plus. So this is one of the effects that alternating layers consist of alternating charges. So then what will happen? So what will happen is if we have even number of layers, then we can understand that it will be uncharged. If we have odd number of layers, then the dislocation core will be charged. So what has happened, so we understood this, that what has happened is in the charge of the dislocation core has reversed. So here it was a minus, but in the layer below it, so we will see that it is plus. So this is one of the effects that alternating layers consist of alternating charges. So this is about the edge dislocation. So what is the conclusion of the edge dislocation? That it may either attract or repel electrostatically. So this is all about the edge dislocations. Now we will learn about the screw dislocations. Okay, so what will happen? So here this part of the edge dislocations will be here in this slide, and from here we will start about the screw dislocations in ionic systems. So if there are screw dislocations, if it is moving, so suppose it is moving on now 100 plane and has a this Berger vector. So because we have learnt this right in the previous class. So the basic difference between the edge dislocation and the screw dislocation is that in screw dislocation it is in plane, and in edge dislocation it is out of plane. So in screw dislocation, if the screw dislocation is moving on a 110 type of plane and it will have Berger vector in the 110 direction, then it cannot cross slip onto any other 110 plane, right? So if we have a screw dislocation of that kind, then it cannot cross slip into another 110 plane, and the reason is that that particular Berger vector 100 type is also contained in it. So the main understanding about screw dislocations is that it cannot cross-slip onto any other 110 plane, and a 110 Berger vector can be contained on only one 110 type plane. So because this we know that the displacement is parallel to the Berger vector, means that there is no relative change in position. So now we will come to super lattices. So what do we mean by super lattices? Yes. So what do we mean when we say super lattices? So we mean that we call it as a super lattice whenever we have two or more species present and they are in an ordered structure. So the first thing that is that when we talk about dislocation in super lattices, then that means that there is an ordered structure of two or more species. So there is an ordered structure of two or more species. So we will understand in more detail what we mean by ordered, but for now it is just that there is a specific position for each of the species, and that is what is meant by ordered species. There is a specific position for the elements. Okay. So what happens is that there is, so pardon my handwriting, there is a specific position for the elements. This is what we mean by super lattices. So we will learn about the dislocations in super lattices. Before that, so we will learn about the different types of super lattices which exist. So at first, the very simple one which exists is the B1, so which is the interpenetrating FCC lattices of Na and Cl. So here suppose this one is the Na, this one, and this one. So this is what is not correct if we write only Na. Why? Because this is an ionic system. So what we have to write? We have to write Na plus Cl minus. So this is the B1 structure, interpenetrating FCC lattices of sodium of Na plus and Cl minus. So then we have the B2 structure. So what is the B2 structure? B2 structure is two interpenetrating simple cubic structure. So B1 was two interpenetrating FCC structure. B2 is two interpenetrating simple cubic structure. Stoichiometrically, it can be represented by 1:1 or 50:50 atomic distributions. Then we have the DO3 structure. So in DO3, what is the example? So Fe3Al, commonly what we write is, we write as Fe3 but here what happens is the atoms sit on the sides of a body-centered cubic lattice. So this is a body-centered cubic lattice. So here the atoms sit on the side of the body-centered cubic lattice. So here if we consider the total lattice, then it is actually Fe12Al4. So these are the Al atoms. This is Al. So this one is Al. This one is Al. So the atoms sit on the sides of a body-centered cubic lattice. Now we will learn about order to disorder transition. So for this we will take one B2 system. So what is Ni3L? So Ni3L is an example of B2 lattice. So here, you can see from here that the blue spheres represent the nickel atoms and the silver spheres represent the aluminum atoms, and this is the coordinate axis. So this side is the x-axis, this side is the y-axis, and this side is the z-axis. So the nickel atoms go at the face centers. Okay, so these are the nickel atoms. So you see on the top face, this is the center of the top face, this is the center of the bottom face, this is the center of the left face, this is the center of the right face, this one is the center of the front face, and this one is the center of the back face. So the Ni atoms go at the face centers, and what will be the contribution? So each atom will count as half. So we have 6 into 1 by 2, which is equal to 3. Right, and where is the aluminium atom? The aluminium atom is sitting at the corner. So there is 1, 2, 3, 4, 5, 6, 7. So aluminium, so this is the formula for nickel. Then what will be the formula for aluminium? 8 into is equal to, this is actually 3. Into 1 by 8 is 1. So then Ni3. So what we have from here is what we have from here is Ni3Al. Okay, so in this Ni3Al, so we will now try to understand this. So what is this? So this is a B2 structure. Just have some water, just excuse me for 30 seconds. So Ni3Al Ni3Al is a B2 structure and it is ordered. So why it is a ordered structure? Because there is a definite position. Right. Now what happens if we increase the temperature? So if we increase the temperature, then we get something like this. So in the every position you see, so here it is not exactly nickel or aluminum. It is not only nickel or only aluminum. So here at one position, so what is it? So it is 50% nickel, 50% aluminum. Then what does this structure become? So if this is 50% nickel and 50% aluminum, then there is interchanging. So in the corners, so here we are putting the nickel, in the body center we are putting the aluminum. So this will be called as ordered. Now in this case, here what will happen, see the blue here represents that this atom is 50% nickel, is 50% nickel and 50% aluminum. So if we to talk in terms of crystallography, then the structure will be BCC. So we see that there is what we can understand from here. So what we can see from here is that there is no designated place for nickel and aluminum atom. So it can go anywhere. However, what we have to remember is that the overall stoichiometry is 1:1. So each of these atoms have a probability of 50% of being nickel and 50% of being aluminum, right? So what we see here in this disordered structure, as we increase the temperature, so what we see is that as we increase the temperature, then if the structure becomes body centered cube or BCC. Since there is no designated place for nickel and aluminum atom, it can go anywhere. Only because since the overall stoichiometry is 1:1, so each of these atoms, what do they have? So each of these atoms have a probability of 50% of being nickel and 50% of being aluminum. So we end up with a disordered structure. Now this is another example. So this example, so we have understood. So this is an example of order to disorder transition. So this is another example. So this is so this is an ordered L12 structure. So here it is still Ni3Al overall. So the ratio must be maintained, but there is no designated position, which means that now 70% of any of these spots would be filled by nickel and 25% of any of these spots will be filled by aluminum, and this will be called as the disorder, and then this structure will be called as FCC. So this is the ordered L12 structure and this is the disorder structure, which turns out to be what? Which turns out to be FCC. Now overall this is still Ni3. So overall this is still Ni3Al. So the ratio must be maintained, which means that now the 75% of any of these spots would be filled by nickel atoms and 25% of any of the spots would be filled by aluminum atom. Here this is, you have to remember, this is not an ionic system like it was the case for sodium chloride. Okay, this will be called as disorder and the structure would be called as FCC. So how can you characterize the ordered versus the disorder structure? So is there any characterization technique? So yes, there it is. So it is the X-ray diffraction or XRD. So XRD is dependent on the crystal structure. So XRD or X-ray diffraction is a very good useful tool which helps us to understand, which helps us to examine the crystal structures, right? So here since XRD is dependent on the crystal structure, so a face-centered cubic structure or FCC will have a different XRD pattern compared to L12 order structure, because in the disordered structure, there in the disordered structure, what will happen, all the atoms will behave as if they are a combination of nickel and aluminum, 75% nickel and 25% aluminum, right? So this will, so the XRT pattern will be a definite pattern for the disordered structure. On the other hand, if it were the order structure, then it is a different crystal structure altogether, and the combination of nickel and aluminum will give a different cubic system. So it will have a different structure factor. I am talking about the order structure. It will have a different structure factor to contribute to the overall diffraction pattern, and here it will be just like a FCC system. So in this sense, they will give a completely different XID peak profile. So if we take the XID profiles of both and compare, then we can differentiate. So in characterization techniques like extra diffraction can indeed differentiate between these two techniques. Now in extra diffraction, there are again two different type of techniques. So one is the single crystal extra diffraction or XID, another is the powder extra diffraction or XID. So both collect data, both have a detector and extra source, but they collect the data following different phenomena. So either can be used like single crystal extra diffraction or powder extra diffraction. So now we come to the question that can material strength increase with temperature? So we will come into the ordered intermetallic systems, but before that, let us understand that why we are actually trying to study the dislocation. So why we need to study dislocations? So the purpose is that the purpose has always been that by studying dislocations, it will be able to predict, or it describes, or it defines some of the properties of the material. So what type of properties? The mechanical properties of materials. So the purpose of dislocation has always been that will help us to describe or predict or understand some of the mechanical properties of materials. So this dislocation phenomena is one such type of phenomena which is of great importance in engineering. So now we are interested in the ordered intermetallic systems. So, and what are some of the key properties of the ordered intermetallic systems? What are the interesting properties which they show? So one of the properties is that they are high strength. So they have higher strength compared to a simple FCC or BCC system, and that too at room temperatures. So what are the key properties? So one of the important properties of intermetallic systems is that they show higher strength compared to a simple FCC or BCC system, and that too at room temperature. And if the system is appropriate, like in some of the particular intermetallic systems, then you can even see that what happens as we increase the temperature, the strength increases. So the strength actually increases with increase in temperature. So normally, what is the nature of shear strength versus temperature? So normally, the shear strength versus temperature is like this. It can be like this, something, two different materials. So this is the shear strength, the temperature. So the usual plot which we would expect is that the strength of the material should decrease, and that is what we expect for, and we also observe experimentally for simple systems like FCC, BCC, or even a disordered system like a BCC system, like disordered, so this will be Ni3Al. But what about ordered systems? Now, if we look at ordered intermetallic systems, then what we see is then it shows what is called as yield anomaly in case of ordered systems like Ni3Al. If on the other hand, if we look at Ni3Al, then it shows what is called as yield anomaly. So here what we see is that the shear strength is increasing with temperature, and it can be as high as 800 to 1000 Kelvin. So close to 800 Kelvin, you can see that there is increase in strength, and only after, so this will not be Celsius, so this will be Kelvin, I will correct it. So if we look at ordered systems, this will not be Celsius. So we see here that the shear strength is increasing with increasing temperature, and then around 800 to 1000 Kelvin. So you see that it increases up to here, say to 800 or 850 Kelvin, and only after that it drops. But before that critical temperature, there is an increase of the shear strength with increasing temperature. So this is called as yield anomaly. Okay, so this is called as yield anomaly. So it has some applications also. So mankind is very clever, right? So when we observe certain things, we study their properties. Why? So that we can put anything to our advantage. So if we see something and it is something is causing a disadvantage to say X, then it can be turned or tuned into an advantage for another system Y. So here what good has come out of it is that we are able to make the turbine blades which operate at high temperature, and these turbine blades are made up of this kind of superalloy systems because they have strength even at this high temperature. So this behavior, which is termed as yield anomaly, here what happens, as we increase the temperature, the strength increases and then it starts to drop. Now the question is that why does the strength drop? So according to the stress requirements that are in this over here, in general high temperature causes lower stresses. What happens in general at higher temperature, so as we increase the temperature, then lower stresses are required to keep deforming at the same rate. Thus, strength decreases as the temperature increases, but not for this particular material, which are the superalloys. Okay, so here in this system, this Ni3Al, over here it looks like the FCC, but it is not FCC, it is L12 structure. So we have seen, so here nickel has a separate position and alumina has a separate position. What is the glide plane? The 111 is the glide plane and A by 2 110 is the lattice vector. So you understand, so this will be the lattice vector and 111 is the glide plane, right? So this leads to what is called as the chemical stacking fault. So in the dislocation, interaction and strain hardening, so now we will answer the question that how does the dislocation density increase. So till now what we have found? So till now we have found something. So we found out how the shear strength of the material increases with increase in the dislocation density. Now the question we will address is that how does the dislocation density increase? So you will thermodynamically what we see. So thermodynamically dislocations are not stable at temperatures below the melting point. So dislocations generate in one plane or dislocations glide on individual planes as we keep increasing the applied stress, right? So we know. Now what happens when the applied stress exceeds than the critical stress? So then what will happen? So what we see is that when the applied stress exceeds more than the critically resolved shear stress of more than one plane, then what happens? Then in such a situation, what happens is more than one plane starts to glide, or the dislocations on more than one plane starts to glide. And what happens with these so many dislocations? So they can interact. If they interact, then that will be called as nothing but dislocation interaction. And in this when the dislocations interact, then what happens? Then they simply, the dislocations, they multiply. Okay, so there is dislocation multiplication. So I hope you understand it. So first thing is that the dislocations are thermodynamically not stable at temperatures below melting point, but we see that dislocations happen in plenty. So this part actually we will cover in the next week. So we will learn about the nucleation. We will learn about dislocation nucleation. So there are various models to explain it, like homogeneous, heterogeneous. Like we will learn, we will address this point, this exact point, that if dislocations are thermodynamically not stable below melting point, then why do we see dislocations, and why do we see so many dislocations? Like dislocations are abundant, right? So there is a reason for that. We will learn that. So what we know is that the dislocations generate on in one plane, or the dislocations glide on individual planes as we keep increasing the applied stress, and when the applied stress exceeds more than the critically resolved shear stress of more than one plane, then more than one plane starts to glide, or the dislocations on more than one plane starts to glide, and then the dislocations can interact, and the dislocations can multiply. Okay, so the origin and multiplication of dislocations. So the question is that, like point defects, are dislocations also thermodynamically stable? And if so, then what will be the equilibrium concentration? So for this we will go to this equation. So this is a very well-known equation. So we all know this equation. Delta G, V is equal to delta H minus T delta S. T is the temperature, S is the entropy, delta H is the energy of formation. Now for delta G to be negative, we can say that at this if delta G is negative at some particular temperature T, then we can say that at that particular temperature T, it is a thermodynamically stable phenomena, or thermodynamically stable quantity. So we when we equate this, if we differentiate it and put equal this, and if we equate this, we find that the temperature T required must be very high. So in almost all cases, what happens is that this T goes above the melting point of the material. This implies, then what will it imply? Then it will imply that the dislocations are thermodynamically stable only at temperatures above the melting point, where the crystal structure does not anyways exist. Right, so this is from the thermodynamics point of view. Thus, from thermodynamics, what it says, so it means that dislocations, it means that dislocations are not thermodynamically stable, at least until the crystal structure exists. But then the general consensus is that then under ambient conditions, why is there dislocation? So what is the reason? That is because no matter how like no matter in what way or how we have created our material, even if it is a little bit large or decent amount of size, then there will be enough stresses inside it that dislocations will be generated. So this is the qualitative answer, that no matter how you have created your material, if it is even little bit large or decent amount of size shape, then there will be enough stresses inside it which are called as internal stresses. There will be enough internal stress inside that material that dislocations will be generated. Whenever materials are not stress free, then it implies that dislocations will always be present whenever materials are not stress free. So this is very important to understand, that whenever materials are not stress free, it implies that dislocations will always be present. Undesirable strain hardening. So this part we will come later. So this work hardening or strain hardening means this dislocation multiplication can lead to strain hardening. So an example, uh, just one thing. So here we are learning about the thermodynamics of dislocations and everything. So this we learn that there will be dislocation multiplication, right? So we will have dislocation multiplication, and this dislocation multiplication can lead to what is known as strain hardening. Okay. Now so work hardening is another term for strain hardening. It is sometimes it is desirable, so sometimes it is undesirable. So here we will see we will see just one example where and when it is undesirable. An example of undesirable work hardening is during machining, when the early passes of a cutter inadvertently work harden the workpiece surface. Then what happens, then the cutter causes damage to itself, and the damage to the cutter harms the later passes, right? So this is an example of of undesirable work hardening, where the early passes of a cutter inadvertently work harden the workpiece surface, causing damage to the cutter during the later passes. So now we will move on to some assignment questions and answers. So what is the shear strength of defect-free material? So if we consider a perfect perfect lattice, then what comes is the homogeneous nucleation model. Okay. So if there is a perfect lattice, then we consider the homogeneous nucleation model. So we have this uh, big equation, right? So do we like go into the details of the equation? So there basically we have the energy created, the energy required to create the dislocation. So here it is a function of the radius r minus some function of the radius r square. So here if we now differentiate it, so if we differentiate it, then we get that the shear stress, the shear strength one second. Yeah. So what we see is, we see that the shear strength required for defect-free materials comes out to be G by 10. Okay. So this is the answer here. Now we move on to the second question. So what is strain hardening? So what is strain hardening? Is it the increase in ductility and plasticity of a metal, or what is it? Is it like I'm reading out the second option, increased hardness accompanying plastic deformation? So you see then the third option is decrease in tensile strength of the metal, and then option D is decrease in yield strength of the metal. So although these terms, plasticity, hardness, toughness, tensile strength, yield strength, ductility, so although these terms may sound similar and there might be a correlation with each other, but they are not the same. They in mechanics, when we study mechanics, so these terms cannot be used interchangeably with one another. Okay, so what is strain hardening? Strain hardening is defined as increase in hardness of any material accompanying plastic deformation of metal. So yes, strain hardening is increased hardness accompanying plastic deformation of metal. So this option. Then the third question is that now we have understood that materials become harder due to strain hardening. Now strain hardening in case of steel. So strain hardening in case of steel occurs because of what? So here the answer is this. Occurs in between the yield strength, the strain hardening occurs. So if you follow the Hooke's law, then from the graph of stress strain, so the strain hardening occurs between the yield strength and the ultimate strength. Okay. So here question 4 is, which term is different from other options? So we have strain hardening, we have dislocation hardening, we have cold working, and we have work hardening. So they may all seem similar to you, right? But one term is different from the other option. So I'm going to give you some time to think about it and tell me the answer. Okay. So the answer is dislocation hardening. Okay, so dislocation, so strain hardening, cold working, and work hardening, they are all similar. Okay. Now, during uniaxial tensile testing, so in uniaxial tensile testing, what happens? We have a metallic part like this. one axis, preferably along the middle axis, so there is a stretching. So during inaxial tensile testing, when does the necking start? So the answer is ultimate tensile strength point. So the necking starts at ultimate tensile strength point. And then where does the plastic deformation start? So the plastic deformation starts at the yield point. So the plastic deformation starts at the yield point. Now the last question. Yeah. So the stress necessary for plastic deformation. So the stress necessary for plastic deformation increases due to elastic properties or strain hardening, all of the above or none of the above. So the answer is strain hardening. So the stress necessary for plastic deformation increases due to strain hardening or what, or cold working or work hardening. So summary, so what we have learned. So if we go back, so we learned about so at first we learned about the ionic systems. So we learned about the ionic systems. Then what? So we learned about the superlattices. Then intermetallic. So you remember, right? So here after the ionic systems we'll learned about the intermetallic systems. So after we learned about so superlattices, we learned about the intermetallics. Then we came to the phase transitions and the dislocation interactions. Came to the dislocation interactions, the multiplication of dislocations and multiplication of dislocations and strain hardening. So strain hardening and finally assignments. Okay. So that's all. So next week we will learn what we will learn about dislocation interactions and nucleation, and we'll go into more details into the origin of nucleations. Okay. So thank you for today's class. So I am going to stop the recording. So thank you.